Eterna and NUPACK code base, recent additions and plans for the future. I will, before I go any further, also say that Jonathan is the lead developer. I'm just kind of maintaining the folding model side of things with my background and that stuff, and just been deep in it, using that folding models for my entire time doing RNA stuff. So this is all stuff that I want to do, not necessarily that has been approved by the lead developer, and actually have a section of like my wish list if I could get anything approved. But this is what's been going on and what's happened, and plans that I've voiced all of these, I believe, and Jonathan hasn't said not to do it. So, but I figure it's been a while since we kind of went over what is NUPACK, and I just kind of wanted to give you guys an overview before I kind of went into like what was done. So it's one of the primary folding engines or folding models that we use on Eterna. The NUPACK team from the website, they call it a growing software suite for analysis and design of nucleic acid structures, devices, and systems. And it's really cool because you can actually do a lot of analysis, and you can even do some design features type of things. And they've actually been improving, and they're on actually version NUPACK 4. But there's some reasons why we can't use that yet. And also, I mean, it's a great software suite actually, and it's like one of the only ones that can do some of the things that we need done. You can find it at www.nupack.org. There's a web application for all the things that I'm going to be talking about, and you can also download the source code. And NUPACK is backed by multiple peer review papers. Here's all the papers that they cite during their just all the different things that they do on the website and in the source code and stuff. These are all the papers I referenced. There's some definitions of terms used by NUPACK. This is basically almost directly from their website and their manual. I felt like putting this in here just to kind of, I don't know, maybe explain some of the terms. I don't know if it's really necessary in the context of what we're doing, but it is important. And some of the things I want to make sure that the community is aware of when we're dealing with oligos and stuff. So it's kind of, the only real main part is like line item 4 or 5, but basically NUPACK algorithms. NUPACK does all its algorithm work against the secondary structures, which it runs mfold to get the partition function, and then it does its stuff to do everything else. It's pretty good software suite, if I think I'm saying that the right way of how it does the folds. Now, a secondary structure, it defines as one or more interacting strands that's defined by a list of base pair. Now, if you're familiar with arcplot, a Palmer graph is basically what arcplot is, and you can really define a secondary structure as like being able to draw each nucleotide as a strand in a circle, and all the all of the connected bases have straight lines. And if it's, and then, you know, to take that definition a step further, unsidered knotted means that there's no crossing lines, and sidered knotted means that there's crossing lines, and that you would see that in the arcplot stuff. Well, you get down to where complex interacting strands, and this is directly from their thing, and this is basically where you start getting complexes, as where you get multiple sets of strands. Now that's oligos. We just Oligos is an explicit example of that. And in NUPACK 3, they call that an order complex. In NUPACK 4, they actually don't call it an order complex anymore. But I left that in here. So now, and then keep in mind that complex thing, because that's going to come up in a second. And now the free energy, the last little note is the free energies are calculated using the nearest neighbor empirical parameter sets that are from like all the standard papers there. There's Sierra and Turner, 1995. That's, I believe, is the basis of that's the paper that defines the parameter set that we use for all our foldings, because we use RNA in 1995, which is the year of the paper that's based off of. I like to use RNA 1999 generally because it's a newer version, but it's set at 37 degrees Celsius is what their work was all done at. Now, if kind of making a jump here now, this is like NUPACK's basic functions and what NUPACK does. So this is like, I want to tell you guys this so you guys know what NUPACK can do, because I want you guys to tell us what we need to do. And if there's something that we need, you know, the squeaky wheel gets fixed. And we can put a bug fix, we can put a feature request in and start tracking these things. So you have, I'm just gonna go through the list real quick and just quickly just describe. So you got pfunc, which calculates the partition function, which is a single value. I believe I don't use that much. I'll understand it a lot, but I think it represents the Q value. It's difficult to explain. I'm not a super expert in all this stuff. I'm getting better and better as time goes on. You got MFE function, which you get the minimum free energy secondary structure or structures, because if you pass the degenerate when you do that, which I think is kind of funny term, you actually get all of this secondary structures at the minimum free energy state, or energy value. You got subop, which finds all the secondary structures within a specified free energy gap. We refer to those as all the alternate structures that an RNA sequence can take over the entire range of energy potentialities. You got count, which actually counts the number of secondary structures are in the entire ensemble. Energy, which calculates the free energy of a secondary structure. Probabilities, which calculates the equilibrium probability of a secondary structure. I want to play with that because I think that might be important. You got defect, which calculates the ensemble defect or the MFE defect. Complexes, remember how I mentioned complexes before? This is important. Calculate the partition functions of all strand complexes up to a specific size, up to a specified size, including pairs, MFE, and other stuff. So complexes is something that you can get accurate pairs and MFE from multiple strands, starting to like, because you can do that with MFE and not run complexes, but it's not 100% the same. And you can actually run complexes and you can get some more stuff. That's what I use in all my papers and all the stuff I did for the paper. So concentrations, which calculates the equilibrium concentration of each complex in a dilute solution. So that is, say you were doing some testing and you wanted to predict what two different concentrations of two different oligos would behave in a test tube, which is exactly what we do with open TB. Is we're testing for concentration, which is the ratio of certain oligos, and that's what we, and I use that and complexes together for all the work with the open TB stuff for the open for the PNAT stuff. Distributions, which I have not played with, and design. Distribution is calculated the equilibrium population distribution. I don't really understand that. And design, which is what I was talking about, you can actually say, hey, I want to make a simple, here's a simple target structure, make me an RNA structure that meets that with, kick out a sequence. So that all being said, a cautionary tale of oligos is the title of this slide. It's actually called a cautionary tale of, called a cautionary tale of energy or something of complexes in the actual NUPACK documentation. So if you're doing stuff with oligos, it could be hazardous to do those calculations by hand and not use the way NUPACK has coded up. And by when you see complexes, really read that as oligos in our application. And a couple reasons for that is it's common to forget the concentration of the H2O, the PHCO. So I think that's the pH value of the H2 of the water. I'm not familiar with that. Somebody who goes chemistry will know what that is, but that's something that needs to be considered. And if you don't, you can have what they say is a seemingly unlimited number of complexes, which can result in a coupled in systems of coupled nonlinear algebraic equations. And it's just, the math is insane. And basically, if it can be insane to validate any custom implementation of that. So NUPACK basics, the way they do it, they say that they take care of it all and they handle it all. So just trust the way they do it. So currently available to Eterna players. So the state of Eterna NUPACK now. I've been in the code base for a while, fixed a couple things. The state of it of the Eterna of Eterna's NUPACK is we have access to MFE. We can only get a single secondary structure though from what's coded up. We can't do a degenerate. So we can't get all the secondary structures at that MFE energy. We can get subop. That was just recently added. There was a bug fix to address a bug implemented at time of implementation. That's been fixed. We can get pairs. We can get pairs. That's very easily accessible. That's actually what you see in the dot plot. It's created from pairs. You can also get that in Eterna script. You can get all the other ones in Eterna script too, but just thought I'd mention that. Defect, that's the newly coded up. You can get a stumble defect in the MFE defect. That's available in the same call as subopt. I'm gonna separate that out later on. And we can get energy. That's what you see in the game for the energies of the stacks and the free energies of the structures. What I plan to implement is complexes and concentrations to provide for oligo data, to provide proper and more accurate oligo data when we get there. Count, so we can see the number of secondary structures, because that, I mean, the number of alternate structures that would be important. I think I used to not care about that, but that's just my own personal stuff. And you guys, I'm trying to not let my personal thoughts influence things. So I'm trying to make sure you guys know as much as possible so you can inform me, and then I might have some thoughts on it. Then also I want to implement MFE degenerate. I honestly might do MFE degenerate as the second one, or maybe even the first one, depending, because it's actually a low hanging fruit. Wish list. I would expose the ability to handle dangles differently, however we wanted. There's 3 options we can use. We currently only use one option. And then also, I would also like to expose the multiple energy parameter sets, which is the RNA 1995 that I mentioned, which uses M-fold 2.4, which allows any temperature. RNA 1999 uses M-fold 3, which is a newer version. I don't know what the differences are exactly, but they only use 37C. Well, it just so happens we only do things that are 37C, so why aren't we using 1999 anyways? That's something that I would strongly argue if we don't allow temperature changes that we, at least allow for variation for that change. Because all the stuff I've done for all the PNAS paper stuff was all done with RNA 1999. So, uh, bugs. Okay, state of Eterna NUPACK. This is where we get into the code base. Bugs. We recently fixed a couple bugs. The team addressed the lack of curly brackets in the sub-op peanut results. That was addressed because I did not realize that there was a separate method for implementing building the secondary structure from the fold for peanuts versus non, and being new into the maintaining the code base. I implemented just the normal, where it's just only expecting a regular structure, non-peanut basically. So implemented the code that was used before for peanuts to address that, and that did fix the curly bracket thing. But the next item down, the curly bracket fix exposed a bug that was in the previous code that we had just identified the date earlier as a potential vulnerability when I did that work to implement that code, because I created a function. Basically, the code base is was not maintained very well at the very start, and it's been getting a lot better. Jonathan's done so much for it. It's awesome. And he's helped a lot with what I've been doing in this stuff. And so created a function, and I went through and understood it completely, but there was one item that I didn't understand that seemed weird, and Jonathan saw something even weirder in there, and that was that issue. And so he actually wanted me to do a test case. Didn't get around to it. It was next on my list because we had put that bug on the back burner because it didn't seem like it would pop up. And then Jill was like, "Hey, I got a lab that did some weird images, some weird data." And we looked at it like, "Hey, that's the test case. It failed." And so Jonathan fixed that really quickly. So that's pretty good. And so we've shored up the rest of Eterna code base because of that as well. To structures are more consistent and reliable there. Existing bugs that exist right now, we have oligos are reporting incorrect energies and some when in pass the multifold function. Basically, you get some weird energies and some zeros and weird numbers. Debugging that right now. The current implementation of new sub code now takes a long time to run. After the bug fixing the feature upgrade, that's where I included a sub-op and defunct and defect in the same thing, and it's just doing a lot of calculations. And I'm not, it might even be because of that curly bracket fix, which is very time intensive, and there might be a penalty there. So that's a bug that needs to be addressed. But if people aren't yelling about it, it's not going to get fixed very quickly. Just time wise. Eternal script for sub-op ensemble defect takes 2 clicks around properly. Jonathan gave me a fix for that. Probably that new window. I'll try to address that, and then maybe we'll be able to have a function that players can use to quickly like tie in any scripts to a new window. Got a couple items left. State of some big endeavors. So to expose complexes and concentrations to Eterna code base, this is going to be an endeavor. The problem is that, as I said, Eterna doesn't give 100% accurate folding and energies for multi-strand sequences. It gives accurate, but not 100% accurate based on concentrations. If we don't care about concentrations, then you don't need complexes and concentrations. But if you're looking at various levels, this is going to be needed. So if we do open TB kind of stuff ever again, this is needed to be completely accurate. Now, adding complexes alone is basically the same as coding up NUPACK from the start, because there's complexes, there's concentrations, and there's basics. And everything we do right now is in basics. So basically coding up a whole new functionality and a whole new like everything for NUPACK. But lucky. We are lucky in that we've already done NUPACK. We have I mean, it's already 80%. Our job is 80% done. We just gotta copy what was done for the entire basics for the entire current NUPACK code base and just add that, but not to the extent. And so we do that for concentrations and for complexes, and we'll be able to do this. I don't know what that's gonna do for time. Jonathan's probably gonna hate me if I try to do this. Um, so yeah. Um, here's the big problem, Endeavor. Eterna enhanced pseudonut algorithm for NUPACK energy model. NUPACK team, they purposely only developed the NUPACK, the PNOT algorithm to be able to understand a specific subset of known PNOTs that appear in the wild. And they say that in the papers and they back that up and they shows up a couple times. So we can only really do peanut stuff that's previously understood, sort of. So Jonathan right now is doing some thing with the pilot. It's a pilot for a reason also, but we can't really move to further projects until, or some of the more complex stuff until this is addressed. Well, and also, if we ever want to go to NUPACK 4, they took out support for PNOTs. So they even took out the code that doesn't work right for us. The thing is that that gets fed into NUPACK, and if we were to code our own algorithm, we could just feed that to NUPACK 4 or NUPACK 3. Well, that's where the problem is. I wrote a PNOT algorithm that I think will work, but I just don't have time to test it out. There's so many other problems, so many other things that are so much higher priority, and I got to debug. So basically, we need help. We need volunteers. We need people to test, validate, and improve it, because we need to both test it, make sure it works, and then validate it, run it through its paces. I mean, some major stress tests. Like this is a full project in itself. We need people. Um, all all hands on deck kind of thing. Please help. And so, using NUPACK to understand the ensemble. This is kind of where I was trying to get kind of preparing you guys to now talk about my mechanics thing, but also wanted to kind of give you guys an understanding of how NUPACK is used to understand the ensemble, because that's really, I think, an important thing that we need to understand more, and that will help us make more advancements more quickly. And that I have seen, and I fear that we are stuck in the MFE frame too much and don't realize or look outside and realize that there's a lot more. So the ensemble is a term that's used to represent all possible alternate secondary structures that a sequence can take in respect to its free energy. Now, imagine if you were to move from the MFE, which is the lowest theoretical energy state, and you moved up, your number of possible alternate structures that it could take increases, so imagine, and by saying that, I was talking to Astro about this earlier, but imagine that you had a list of 4 different alternate structures, 1, 2, 3, 4. And the first structure is -30, and that's your MFE structure. The next structure is -25, next structure is -20, next structure is -15. And that's basically what you would see in the sub-op list. Now, what you actually see there, that's telling you if the structure, if the RNA for some reason is at an energy level of -15, it should have the structure of line item 4. If it happens to have an energy value of 25 at the time, it should be at line item 1. But each energy value is what that RNA sequence, the structure it should take when it's at that energy. How it gets there, that's up to the RNA. But I like to think of it as temperature. because a temperature is a major variable that controls the partition function calculations of M-fold. And so as temperature fluctuates, your energy changes. As your temperature rises, your energy goes in a positive direction. Fractions of a degree and you get energy shifts. I'm not sure what extent, but I'm sure it's significant. I'm thinking. You go colder and you go down to negative energy, which is the whole thing with COVID vaccine. The the RNA sequence that's been designed has such a such a high melt point, as to be stored at such a low temperature so it doesn't tear itself apart. But yeah, and so as you're doing this, as the temperature changes and as your energy levels increase and change, pairs that were once strong at one temperature at one energy level are now weaker at another, and vice versa, just because you got this the pairing probabilities are shifting because your equilibrium state's shifting. And just this is where I get into the mechanics, is really just the forces. Pairing probabilities are just forces, really, or representation of forces in a really rough, rudimentary way, not accounting for some things. And you're just looking for an equilibrium state. Well, that equilibrium state, if you have a different temperature, means you have different pairing probabilities, which means you have a different structure, and you're gonna have some weird things. P naughts might cause you to have a different fold, because a P naught might form now in one energy level, but not another. And so those alternate structures can be different by orders of magnitude, or it can just be the exact same. And that's where you get your MFE defect kind of stuff. Or Astromon showed me a structure, a design that I think its MFE state was like -45, and there was a energy state at -42.2, where there were 5 different sequences at -42.2. The exact same delta, exact same error, and they each had a fairly significantly different the chunk of the structure that was fairly significantly different. And if that design ever hit that energy state, that would be a mess. And so it's just like, that doesn't seem very stable. So you can learn so much from the ensemble. Kind of peek behind the curtains, if you will. And actually, that's that peek behind the curtains. I'm gonna kind of jump real quick to the third item down, MFE degenerate. How I said earlier that MFE, that the fold uses M-fold. Well, if you go to the website, so M-fold has been replaced by unifold, which actually does M-fold in an algorithm for melt point, which is the same people who did M-fold do unifold, and their website has a thing on M-fold saying, don't trust M-fold MFE structures. Look at the energies and make sure, because M-fold just gives you the most common structure sometimes, or the lowest energy. It may not be the most common. So you might have, so yeah, it's something that it's like a note for a note for a note that I feel like somebody should have put in like bold letters somewhere. But NUPACK, we have access to the ensemble through NUPACK, through subop, MFE, the degenerates option, count, pairs, and defect. Subop, as I said, displays all the alternate secondary structures. MFE degenerates displays the alternate structures at the same energy level as the MFE structure, as I said. So if the MFE was -37 and there was 4 potentialities at 37, MFE degenerates would give you all of them. And that's something that you would want to use kind of if you were to make sure that it was the actual true MFE. And I think that's something that would be fairly important to expose next. Count displays the number of alternate structures in the entire ensemble. Pairs lists all the pairing probabilities. I mean, that's kind of low hanging fruit there. I mean, it displays the pairing probabilities, whether or not it's you're looking at the ensemble or not, but pairs is kind of like your raw data. And defect displays the ensemble defect and the MFE defect values that represent the amount of variation across the ensemble at the whole level, at the structural level. And just kind of get to the where like I have a metric that I've developed that I've called ensemble variance, which people have noted quite accurately that it's pretty much the exact same as ensemble defect. The only difference is ensemble defect looks at the entire range across the entire energy deltas, and my ensemble variance is almost like an instantaneous when you look at each what it is at each delta specifically at that point. And when you get past like 4 or 5, it looks the exact same as ensemble defect. Just want to give that quick note because I'm going to be including ensemble variance in one of my scripts soon, just so you guys can understand. So you're not blindsided by what's this? Like ensemble variance can be thought of like an instantaneous value of how stable it is structure is at a specific delta from the MFE versus overall. And yeah, so I got 10 minutes left, which definitely is not enough time to do my mechanics thing. So any questions?
Reju asked, did the NUPACK authors state at all why pseudonauts were dropped in version 4?
No, they did not. They just said it's not supported anymore. But
I feel like I tried searching for it. I could have sworn I saw something about it. In I don't know if it was a paper or if it was in a documentation somewhere that I can no longer find. I'm not sure. I feel like it was some issue of it was just too complicated, like the additional complexity it added to maintaining the code, and they didn't necessarily feel that they were able to it was able to be good enough to be worth it or something like that. I could be completely making that up. I swore I read that somewhere, but don't quote me on it. And another thing that I will mention about there's discussion about different types of pseudonauts working versus not. This is something that Jennifer and I have talked about before. I'm not 100% convinced because the issue that we see is only in calculating energy values, not in actually generating the MFE structure, right? NUPACK will give us an MFE structure that includes pseudonauts that we can't calculate the energy values for, like it crashes. Which makes me think that, I mean, it says that it's an unclassified pseudonaut, but when I was actually checking the logic, I'm like, it looks like it's just not enumerating pseudonauts correctly, right? And we started kind of going down that rabbit hole and wound up finding issues in other places. So I'm not 100. I'm personally not completely convinced that NUPACK can't give us energy values for the things that we're looking at. I think the implementation is not right. And Andy seemed to agree with me when I talked to him about it.
yeah, and
But,
I think I have some disagreements on that a little bit in that I think, but I mean, this is another area where we need to actually run the stuff. But like, I do agree with, but I think that this, I might be thinking of a different area in the code, but like, I think that the main area, like what Jonathan said, was that NUPACK isn't instantiating these are the peanuts right. And I'm not completely sure it's ever worked because I don't know what they use to test it against. But looking at the code, I think it should walk it fine. in theory. And so like the logic I wrote this entire function in C to replace NUPACK's implementation. And if this works, I think we could use it so many places, I think. And what it does is it actually walks the structure, and when it sees, so it walks the RNA strand, and when it sees a structure, it goes, hey, it does some stuff and goes, hey, is this, it knows where it is in the structure, in the sequence. And then it starts asking questions and it starts poking and it goes, oh, wait, I'm expecting anything ahead of me to be in this range. Well, this is back here. Well, let me keep track of this. Let me look a little bit. Oh no, yeah, I went all the way around here. And so it basically in theory looks at just the structure of what you're in, and in theory should build a complete list of all the P knots, which is what they're trying to do kind of. So what they're trying to do in the NUPACK implementation is they're listing the beginning pair of each P knot, so that when the RNA, so when it walks the F energy sequence and then the FB, and when it walks that, it goes, oh, is this the start of a P knot? Yeah, it is. Okay, let me do this extra P knot bonus. Okay, I'm done with that P knot. Yeah. Okay, let me start back with where I was. But it also makes sure that it, because of how it's recursive, it's designed that if no structure should ever be hit twice, if it's the same energy structure. So like index 1, 2, and 3, index 3 shouldn't be hit twice. And if it does, it screws up the entire calculations. And so it's got this special recursive method. And so that is, I think, where the murkiness comes from in that. And I think that the function I wrote should work. I got it to build. I haven't debugged it yet. I'm scared and I ran away. Cause it's C code and pointers everywhere.
I'm looking back at some of the questions.
So I'll say a couple things while you look.
Yeah.
So you mentioned wanting to model more complex peanuts. I don't think we need to get that far out. I think that can wait. Like we've got a lot of pseudoknots that we can make currently in the current lab and enter a lot. And I don't know that we need to be thinking too much about the more complex peanuts right now. I think that might be more down the road. Another thing you brought up was you wanted to ask players, do we want a separate script for the metrics? So currently when I run the script, it takes about 10 seconds to generate the ensemble. And when we add the metric, what does it take, more like 20 or 30 seconds? And so I think you were wondering whether players wanted a separate script for the metrics.
Yeah, I'm asking if it's taking too long, because I don't, it's, if it takes too long, people aren't gonna use it. And it's bad enough they have to click twice. So, but also we've been known to have those long clicks problems, and so we're kind of used to it. So I'm inclined to just jump on that and make that my priority to fix, because it does not seem like a good user experience. But also, if no one cares, then I have other things to work on. 'Cause
So
that-
so just people know the script, you could just go do what Bob showed us this morning, is go into the script and you'll see the peanut one right there. It's a very new script, and favorite it, then you can go and use it in the game, in the lab puzzle. And it now has the metrics in it, I believe.
Yes, it has
Yeah,
the
yeah,
ensemble
there's
diversity
yesterday.
and the ensemble defect. And it's also got the normalized values that Eterna, that NUPACK creates.
And hopefully maybe this next week you could write something up and put it in the forum explaining what those metrics are.
I could. Yeah, I will work on that. I'm trying to force myself to take a breather from all the work I've been doing, because I've been on disability for a few weeks now, and I've spent my entire time doing the NUPACK coding. I spent I spent like 2 weeks coding up all this new stuff, and then Jonathan very smartly goes, this is a lot of changes, explain them. And I'm like, I can't. And he's like, well, then I'm not doing it. And so I had to basically pull everything back and redo everything in a way that we already implemented that I could explain better.
So maybe I can write something up of my understanding and run it past you for correction.
Yeah, that would honestly be really great. I really would appreciate that, just because
Okay.
I'm exhausted lately and I've
Oh,
got so many
good.
other things.
You've done a lot of work.
And Jill, you had posted a question earlier in the chat about if the sub-op script is providing the same information as the dot plot would, but a different format. Jennifer, I don't know if you want to talk about
Sorry,
that.
what was
or
that? I missed that.
if
I was reading something.
the relationship between the suboptimal structures and what you see in the dot plot.
Oh, yeah. That kind of goes into the mechanic stuff and a little bit more of the stuff. I wish I had shown that a little more. The relationship is that the dot plot shows all the pairing probabilities of every nucleotide pair, regardless of whether it is supposed to pair or not. So if you have 7 nucleotides, you have, was it 7 to the 7th power, I think, or 7, it's however many combinations you could have. That's how many different pairing probabilities you would have listed. And so it'd be like 1, 1, 1, 2, 1, 3, 1, 4, and it would have, like 0, 0, 0, 0.1, 0.1. And if you see like 0.9, if you see a 1, that means it's like a glued on there with super glue. And if you see like a 0.1, it means, they got some like Scotch tape on there. And so like, that then you can look at that and say, well, we got all these. If you look at all the 0.9, 0.8 to 0.9s kind of thing, that will basically be your primary structure. Like that, I mean, that will basically match your secondary structure, like your pairs. And as you go down and as your probabilities get lower, that means it's less likely to happen, which also means, but if you think about it, if you increase your energy to be more positive, it becomes less stable. So those bits, those pairs, those probabilities that are like hidden in the murk become stronger, because those are the potentialities of it's a potentiality. So when I said, you could have pairs that are stronger in one state than weaker in the other, like those, like when you're looking at the dot plot, those really dark black ones are really strong pairs and really light gray ones are really weak pairs. Well, at negative 37, this nucleotide will be really dark, but then at like 15, it's light and the other one's dark. When it was light before, you have this complete shift. Well, you know how we've seen sequences, designs that'll just flip and do some weird stuff, right? Well, that's exactly what's happening, because we've now introduced that little change. You have that one little, those designs where you change that one RNA base to something else, and the whole design something completely different. And that's why.
Well, okay, we put it this way. I don't know that we really need dot plot when we have the sub-op script, because the sub-op script data is probably superior.
Not necessarily. I think it is two ways of looking at the same thing.
Yeah,
kind of, right? Dot plot is saying what's the probability of each possible pairing, whereas sub-op is saying, well, here's some concrete structures that could be possible. Right?
Yeah, exactly. Okay. Now, but also, like, you can't have one without the other. It's like trying to take all the hate out of somebody with, or take all the love, you can't, a person is balanced. And so like the dot plot also shows you influences, it's like, yeah, these pairs aren't paired, but they're tugging on each other. You don't see that in the sub-op, but the sub-op shows you what the pairs are going to be. I mean, what the structures are going to be. So yeah, Jonathan, you're exactly right. It's two ways of looking at the same thing. They're connected at the hip and you can feed. So almost every thing in NUPACK, if I remember correctly from the code base that does actions on a secondary structure, you can feed it the pairs instead. It has an you can just feed it the pairs instead of the structure. You don't need to form the structure. You can just feed it the pairs. It does the exact same thing, maybe more accurate, because like when you're doing complexes and concentrations, you feed the pairs to do all the stuff from those to get your, because pairs complexes and concentrations creates a really accurate set of pairs list that you then feed to MFE. I think it's been a while since I coded that up, but so you know, I would say that, and I'll wrap up with this to try to avoid saying the same thing again multiple times, but like the dot plot with arc plot is perfect for when you're looking at like what's the influences, what's going on, you know, where are these pulls, but like looking at the sub op gives you this quick understanding of, because you can just kind of look at it and see all the changes and you can kind of go, oh, you can just, it's so much easier for a quick feel of, okay, yeah, it is stable, but how is it not stable? Like what part really helps you narrow down things, if that makes sense.
Okay, that's all very helpful. So the arc plot was more tightly tied to the dot plot. That's helpful to know. I didn't know that than the sub.
Yeah,
So
the arc plot is a different way of showing the dot plot, basically. Instead of showing it on a 2D grid where you know you go from one side and the other side and that's a pair, it's actually showing the arcs are going between the bases instead of it. So it actually draws a line between the bases as opposed to just having a dot.
It's a polymer graph, I believe is called.
So there are potentially two different tools still that different players can be using according to their preference and be comparing. So that's great. And Riju said the arc plot is great. It's not currently working very well. It needs that script has issues that need to be fixed, and Janerson Lee hasn't had time to fix it. So just let Riju know that.
Yeah, and that's one reason, like I was playing with it, and I think some of that might be is that there's so much, like he's doing a lot of awesome stuff in there. He's creating a lot of like this GUI that's really cool. And the thing is, which is where I was talking about, like most of that code is the GUI. There's not a like he coded it, like he does an awesome job there. And it's like, okay, if the Eterna developers or somebody made a bunch of libraries for GUIs, you could just say, hey, JR, use your awesome brain and spend it coding stuff and not working on a GUI. You know, that's, I think, something to take away on that.
Yeah, and I think the last kind of discussion that I see is around Eternafold. Now, I don't know the details specifically. I think Riju actually has a little bit more insight than I do, but keep in mind that Eternafold is actually based off of a different package called Contrafold. And it's basically just, from my understanding, it's just basically Contrafold with additional data fed into it to be able to make better predictions. I don't know what Contrafold is able to handle as far as pseudonauts. And as far as the specific question that Riv asked was, why is NUPACK being further developed over Eternafold? I mean, to some degree, well, we're not necessarily really furthering developing NUPACK. You know, we noticed some bugs in it, right, that we're trying to fix so that it's usable. And you know, in general, we're just integrating kind of these third-party libraries as opposed to actually actively developing on them ourselves. Eternafold is actually kind of a special case because that is actually something that we did kind of work on in-house. But that's to some degree that kind of stuff is often a matter of who is able to devote resources to this, right? Because that was something that I think actually a number of people in Rishu's lab had tried over time to actually work on, and I believe it was Hannah was the one that finally brought it over the finish line. But we don't really have a ton of resources to be able to throw at working on this stuff, and certainly Thomas and I right now are the only full-time developers, and we're not scientific programmers so much. I've started kind of getting a feel for this as I've been working with Jennifer, but by no means do I really understand what's going on under the hood in any of these energy models.
And I barely do. Like, I know just enough. Like,
Yeah,
I know
I mean,
enough to trust me, sort of.
yeah, and folks like Hannah and Andy and Nando previously, they had a much deeper understanding of it, and it's really just a matter of who we have on hand and what they're able to throw their energy towards.
I want to add, I do have some grand ideas and schemes in my head. I should have added this in the wish list part, but like, I would love to do a Franken engine of like I want to get a hold of Unifold's code because they have an actual algorithm in Unifold that will get you melt point instantly instead of multiple folds to get melt point. It's an actual algorithm now. There's boom, there's melt point, which that would be great for us to have as a metric. I mean, that would answer, COVID problem, hey, is this gonna fall apart? Nope. Cool. And also I want to kind of take their new application to stuff and just kind of slip it into, okay, I've got the secondary structure now. Let's just port that over to NUPACK and say, NUPACK, what are you gonna do with this? So just maybe back and forth energy models or something, some crazy ideas I got. But Jonathan will never let me do those.
We'll see.
Jonathan, did you see what Riju said about thrush nuts?
Oh yeah, so I'll read the comment. There's if scrolling will work. There's a way to use the base pairing probability output of Eternafold with the thresh knots pipeline to get pseudoknots, which is really interesting. That we could kind of take advantage of multiple tools. I don't know anything about thresh knots specifically, but I could imagine that could be something that we could look into. And I think one thing that's going to be interesting moving forward as we're talking about potentially improving on energy models and upgrading new versions and stuff like that. How do we manage and even adding additional parameters, right? How do we manage that in Eterna in a scalable way, right? Where, well, if you upgrade an energy model, does that now solutions people, particularly with challenge puzzles, right? They've submitted solutions. Now they're invalid, right? What if you can no longer solve a puzzle even with a newer version of an energy model or something like that? And and it could be a legitimate bug too, right? Something that we want to see fixed. But I think those are interesting questions that we need to think about: is how do we handle those scenarios in a way that makes sense, from a player's perspective, right? And doesn't horribly break how you use Eterna, but is also maintainable within our code and allows us to actually integrate these improvements and stuff like that.
Because that's actually something that we're actually dealing with daily, that Jonathan's constantly tempering. I'm like, Jonathan, I'm going to replace this entire section with this whole new code that I pulled out of NUPACK. Well, what's different? What happens in our current code? I don't know, but it's completely different. I don't like it. I'm going to do NUPACK's thing. Well, it might break Eterna. I'm like, so I have to understand what it is that I'm about to break. And just want to throw that in there. I tried to do almost a complete rewrite of half the stuff. I'm trying to temper myself. But we need people like John, we need resources. I don't know if I'm jumping in the middle of Jonathan when he's talking, but one of the things that I see as a problem too is if we get the developers, we got to coordinate, we got to get stuff done. I'm working on some resources. So I found working with Jonathan gave me an idea and I looked at it and I'm basically like using GitHub code bases. Basically, if a developer, if anybody wants to help, they don't have to have a computer that can code. They can just have an online account on GitHub, and I'll give you a logon for you. Basically, will have a developing environment in the cloud, and you can do everything in there, and so that actually works. So like that's something I'm trying to help do to kind of make things easier. So just keep that in mind. So.
Thank you very much, Jennifer. Thank you for all your work, and thank you for the presentation.